Welcome to EDU World Space.
Alright guys, we're doing problem number 80 in chapter 7 of Chemistry Central Science. So figure 7.4 shows the radial probability distribution functions for 2s and 2p orbitals. I've drawn that here, where p is our probability of our electron existing a certain distance away from the nucleus, which is d. Which orbital 2s or 2p has more electron density closer to nucleus? That's going to be our 2s. We can see that the biggest peaks for 2s and 2p overlap to a good extent, but also you see a small bump for 2s that's closer to the nucleus, so it does have more electron density closer to nucleus than 2p does. As you can see, 2p has no bump here. So how would you modify Slater's rules to adjust for the difference in electron penetration of the nucleus for 2s and 2p orbitals? So remember what Slater's rules are. Slater's rules are a way of accounting for the shielding of electrons. How much, remember, we have an atom positively charged nucleus and different orbitals of electrons around it. There's attraction between the positively charged nucleus and the negatively charged electrons. The valence shell does not feel the full charge of the nucleus. It's because the inner shells partially cancel out some of the positive charge, so you only feel a fraction of the actual nuclear charge. That's known as your Z effective. So now we can know the degree of shielding as a fraction. So if we so the more dense your electron cloud is, the more concentrated your negative charge is. So that's going to better shield the nuclear charge from your valence shell. Think of it similar to like comparing an opaque layer to something that's opaque to something that's transparent. If you look at something that's transparent, light is coming through. Well, if you're looking at something opaque, something is blocking the light, so it can't flow through. It's analogous to what you see in a nuclear reaction an atom it's analogous to what you see in an atom, except instead of light we have electrostatic attraction, and instead of an opaque material we have electron clouds. And the greater your electron density, the greater the shielding you're going to have. So you can modify Slater's. So for Slater's rules, we have these specific rules. Depending on whether you're at the n level, at the n-1 level, or at the n-2 level, you get a specific degree of shielding. This is going to be, for n, it's at 0.5. For n-1, 0.85, and for n equals 2, it's 1.00. At 1.00, that means you have complete shielding of the nuclear charge. So you can actually modify Slater's rules and say that and not just based on the energy level you're at, you have a certain degree of shielding, but also based on which kind of orbital you have, your S, your P, your D. So you can think of it as for NX, you have this kind of shielding. Whatever that may be. And this is us. Or you could think of it as it's going to be kind of a relative scale. So if you're looking at the degree of shielding the electrons your p orbital are sharing, you're going to have a relative amount of shielding from your s orbital and also the other electrons in your p orbital. So you have to take account of both the energy level you're at when using Slater's rules, and you would also have to take account of the kind of orbitals that you're having. Because since your p orbitals are at a higher energy level than your s orbitals, they're not going to your s electrons are not going to shield the nuclear charge the same way as your p electrons. So both have to be